why this exercise sections you need a different room? Would that be due to this room will be closed?
We may be able to do in that room. I have to
Okay.
talk with clients.
Okay, but up to you. Okay, so I will try to catch up the schedule, and if you really on Wednesday, if I can finish the topics in advance, then I will give you more examples about the thermal loadings, the thermal strength, and the indeterminate process. But now today, I want to proceed on the new sections and called the Poisson ratio. Those materials also available on slides, but I prefer to write it down because I can slow down my pace and can give myself more time to do the explanations. But later on, when necessary, I will go back to the slides. Poisson ratio is this. So far, I have given you the impression, which is not so accurate. That is so not so precise. Is this? So far, I give you the impression is all the material models we've been working on is one-dimensional. Okay, if you could imagine all the examples, one-dimensional, that means if I keep a load in the horizontal direction, we only calculate the horizontal deformation or strength. We haven't considered the corresponding vertical deformation or vertical strength. But in real case, all the materials should be three-dimensional. That means, for example, if you choose the chewing gum, you take it out and you stretch it. And you can tell it's getting longer, but in the vertical direction, you can see that getting thinner, right? And that is taken care of by the Poisson ratio we're going to introduce. So from this point onward, whenever if you think, for example, in terms of the problem statement, mention the Poisson ratio, that implies you must consider at least two-dimensional material models into consideration. Okay, and this will make our work, the model, more practical, more precise. And what is Poisson ratio? If we consider a material model like this, and it has the Young's modulus, and for example, the cross-sectional area everywhere is uniform the same, and it has a length L. And for example, if this is under the point loading like this, and from our previous discussions, we know that this material is going to stretch. And for example, to stretch could be on the two sides evenly. So let me do this way. So basically this amount plus this amount is what we call the delta. And that is PL over EA. That is what we have learned before. And that is the whole story. And now you can see in this drawing, I also drew the material due to the stretching. In the vertical directions, or we call the lateral directions, the material gets thinner. And this amount plus this amount, the two amounts, that is what we call the lateral deformation. This one is called the axial. Deformation. The axial, that means we define the axial direction is in the direction of the P applied. And the lateral, that means in the vertical direction to the direction of the P. The lateral deformation can be calculated by introducing the Poisson ratio. The Poisson ratio, by definition, is the ratio of the strength between the two dimensions. So that means, here, let me write it up. Poisson ratio equal to, by definition, is the magnitude of the strength divided by the magnitude of the axial strength. Okay, so if I take up the coordinate systems like this, so x is a horizontal direction, y is a vertical direction, then basically here this can be written up as this. The magnitude of the strength in y direction divided by the magnitude of the strength in x direction. And in our textbook simply use the absolute value to indicate here the ratio is a magnitude ratio. Because in real case, you can see the strain, the axial strain is getting elongated. The axial strain is positive. The lateral strain is negative because it gets shortened. So here for the Poisson ratio, we just take out of the sign. And this definition is very straightforward. And for most, for all the natural materials, the Poisson ratio, here we use the notation called nu. We use the notation nu, and this is a very common notation in almost all the textbooks. And for all of the natural the materials, the Poisson ratio is less than 0.5 and greater than 0. So that means we always will expect, once we stretch elastic material, we will expect the lateral direction will be shortened. Or on the other side, if we compress, then the lateral direction will get expanded. Okay. This explains the Poisson ratio in terms of the xy direction, and the same thing if we consider in the z direction, we have the same concept here. And let me ignore the z direction. So basically here in general, here I drew is a two-dimensional model, but you should imagine extend this concept into the 3D. So that means once we stretch, not only y direction, but also in the outer board, in the z direction, the material will also get shrink. Okay, and the value nu should be, the constant that should be equal either in y direction or in the z direction for most of the I would say the isotropic or simple material model. Okay. So with those things, then we can use one example to see